Part A of this problem asks us to calculate the capacitance of a parallel plate capacitor with a metal slab of thickness A centered between the two plates. Because we'll need it later in the problem, let's start by writing down the capacitance of a standard parallel plate capacitor with plates separated by a distance d. If we assume a charge of magnitude Q on each plate, the electric field between the plates will look like this, and we know from Gauss's law that the electric field magnitude is sigma over epsilon naught, where sigma is the charge per unit area. This electric field is uniform in space, so the voltage or potential difference across the plates is the electric field magnitude times the plate separation d. The capacitance of this arrangement, which I'll call C naught, is the magnitude of charge Q over the voltage V. The charge Q on either plate is the charge density sigma times the plate area A, and when we substitute our expression, we find that the capacitance is epsilon naught A over the plate separation d. Now if we look at the figure we were given, we can calculate the capacitance of this arrangement in a similar way. We assume a charge of magnitude Q on either plate. The electric field that results will move positive charge to the bottom of the slab and negative charge to the top of the metal slab, so that by Gauss's law we can see that the electric field inside the metal slab is zero. In between the two plates, but not inside the metal slab, the electric field is the same as it was in the previous arrangement. It has a magnitude sigma over epsilon naught, where sigma is the charge per unit area. Because this electric field is uniform, the voltage across the two plates is the magnitude of this electric field times the distance between the two plates, not including the slab thickness where there's no electric field. So that's d minus A. The capacitance is the charge divided by the voltage across the plates. The charge is the charge per unit area times the area. Substituting our expression for the voltage gives us a capacitance of epsilon naught A over d minus the slab thickness little a. As a second way to solve this part, we can treat this arrangement as two capacitors in series, each with a plate separation that I'll show here in green of d minus A over 2, half of the distance between the plates not including the slab. The equivalent capacitance is then given by the reciprocal relation. 1 over the capacitance is 1 over the capacitance of the top part plus 1 over the capacitance of the bottom part. Those are the same, so we can write this as 2 over the capacitance of the top part. The top half of this arrangement has a capacitance, epsilon naught A, over the plate separation. That's shown in green, d minus A over 2. When we substitute that into the series expression above, we get the same result as we did with the previous method. Part B asks us to express this capacitance as a multiple of the original capacitance C naught. To do that, we can substitute our expression for the capacitance C on the left and our expression for C naught on the right. The numerator epsilon naught times A cancels from each side, and we can solve for the constant K. That gives us d over d minus A, so the new capacitance C is larger than the old capacitance C naught by the factor d over d minus A. So the thicker the metal slab, the higher the capacitance.